All right, so in this video, we're going to be graphing exponential functions and then also looking at situations that follow that exponential or multiply type pattern. So here's kind of the generic form for an exponential function, y equals a times b to the x. It can also be written like this here, where we have y equals a times b to the x. Now notice that your a value there, that's your initial or starting amount. It could also be a y-intercept. And then the b, that's your growth or decay factor. That's the amount that you're multiplying by. Compared to a linear. A linear is where you're adding the same amount each time. Exponential is where you're multiplying the same amount each time. So remember, with linear, we had y equals mx plus b. That m, that's your slope or your rate. That's the amount you're adding. Where exponentials, the b value, that's the amount that you're multiplying each time. In this video, we're going to be starting with exponential function and putting it on a graph. And then we're also going to be having situations that follow the exponential pattern where we're doing multiplication and writing that as an exponential function. For graphing, anytime you have a function that you're trying to graph, you can always use a table of values. So to find this blank right here, this y value, you could take this -2 and write it in for x. Then you do your order of operations and put that value in right there. For this blank right here, replace the x with a -1. Order of operations for this blank here, substitute 0 in for x, do your order of operations, so on and so forth. So you can do that like for lines, in this case it's an exponential, or even quadratics. You can always graph using a table of values. But for this video, we want to go straight from the function onto the graph, okay? So now do notice that exponent is a variable. We have a variable in the exponent, therefore we know it's an exponential function. That being the case, it's going to follow this form here. So y equals a times b to the x. So look, the 2 replace the a, so we know that that's going to be our starting amount, or our y-intercept, and then the number that replaced the b, that is your growth factor. So this is a times by 3, or a tripling function, if you like kind of the English better, tripling function. Okay, so now when we go to graph it, we start at that starting value, the y-intercept, so that's a 2, boom, right there. And then when we go over from there to the right 1x, right, we're going to triple that number. So 2 tripled makes 6. And then tripled again is going to make 18, which is all the way off the graph there, okay? So it's a tripling function. Now, we don't quite have enough values on our graph to kind of see the exact pattern, so we are going to go to the left a little bit. So if we're going to the right and it's tripling, what happens when we go to the left? Well, it's 1/3 or dividing by 3. So 1/3 of 2 is 2/3, 1/3 of that, 1/3 of that, 1/3 of that. So we can see here that as we go to the left, it gets really, really close to the x-axis, and it actually will never cross the x-axis. So, but check it out here, right? Multiply by 3, multiply by 3, multiply by 3, multiply by 3, multiply by 3. So as you go to the right, it's always multiplying by 3. And then after you have your dots on the page, go ahead and just connect those with a nice smooth curve. Here we're going to graph y equals 3 times 2 to the x. Notice the exponent is a variable. So we have a variable as an exponent, so it's an exponential function, okay? So it's going to follow the pattern y equals a times b to the x. What number replaced the a? Well, that's a 3, so that's our starting amount, or y-intercept. What number replaced the 2 or the b? Well, that's going to be a 2, so our growth factor is 2. So this is in English a doubling function. So when we go to graph, we start on the y-intercept. The starting amount, well, that's going to be a 3, right? And now it's a doubling function. So when we go over to the right, we're going to double that number. So 3 doubled makes 6. 6 doubled for the next one over is going to be a 12. And then we got a 24, and then keep doubling, right? So we can also look at these going to the left, right? So if it's going to the right, you're timesing by 2. Going to the left, you're dividing by 2 or taking a half of. All right, so going to the right, just to get more dots on our graph here, that's going to be a 1.5 there, and then half of that, and then half of that, and then half of that. we're going to keep on getting closer and closer to the x-axis, but we're never going to cross the x-axis. But check it out. Going from left to right, going to the right, it always doubles, right? Doubled, 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 or times 2 times 2 times 2 times 2. Okay? And then after you have all your dots, or enough dots, you go ahead and just draw a smooth line through your points on the graph, and boom, there's your graph. Here we're going to graph y equals 4 times 1/2 to the x. Look at that exponent. There's a variable in the exponent, therefore you know it's an exponential function, so it follows this form here, y equals a times b to the x. Well, check it out. What number replaced the a? Well, that's a 4, so you know that that's your starting amount on a graph, y-intercept. What number replaced the b? Well, that's going to be a 1/2, so that's your growth, or in this case, it is a decay factor, because it's going to be getting smaller. So on this one here, you're multiplying by a 1/2 each time, so you're halving it. You can also think I'm dividing by 2. So now when we go to graph this, right, our starting amount, that's the y-intercept, that's going to be a 4. So there's that point there. And then as we go to the right, we're going to do half as much. So half of 4, well, that's going to be a 2. And then half of that, that's going to be a 1. Half of that makes 1/2. Half of that is a 1/4. Now, if you think you've got enough dots on your graph to make a good graph, you can. If you want more, you just go to the left. Well, the inverse of halving is doubling. So, right? So 4 doubled makes 8, 8 doubled is 16, right? So that way, as you go to the right, you're doing half as much. So 16, half of that is 8, half is 4, half, 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 half. So as we go to the right, it's always going half as much. And it's going to approach that x-axis, but it's never going to cross the x-axis no matter how far out you go, right? So now that we have all these dots on here, we can go ahead and connect all them with a smooth line. And there's our graph for y equals 4 times 1/2 to the x. Okay, so in this example, we have a tree that we just transplanted. Right now it has 5 leaves, right? Starting out 5 leaves, and then the number of leaves is going to triple every week, okay? So notice we are tripling every week. So this is a repeated multiplication. It's a tripling function. So that is going to be an exponential function. So it's going to follow the form y equals a times b to the x. Okay. So here we go. So our starting value, that's going to be the a, and then the b, that is your growth factor. Okay. So here we go. So instead of a y, we're going to use L for number of leaves. So the leaves equal, now our starting amount, well, right there, it says it started with 5 leaves the day you transplanted it. So 5 replaces the a, and then the b, well, in this case here, it's a tripling function. So the b is going to be replaced with a 3 because we're multiplying by 3 each week. So we can put a w, we can put a w as the exponent instead of an x. And with these ones here, it kind of depends. Sometimes your teacher says, no, you got to use an L and a w, or you can use the y and the x there for your variables. Okay. Now, these equations are a summary statement of the words up here. So check it out. The number of leaves is started at 5 and multiplying 3 per week. Okay, so I can take all of this information, looking at the equation, and I can actually restate the information just by looking at the equation there. Before we get into the next example, we're just going to do a quick review of a concept. Okay, so let's just say, suppose this morning you have all of your money, and then throughout the day you spend 20% of it. So how much are you going to have for spending tomorrow? Okay, so remember, we started the day with 100%. Then throughout the day, we got rid of or spent, we subtracted 20% of our money by the evening. So that's going to leave us with 80% of our money to spend tomorrow. Okay, so this idea of subtracting from 100%, or if you gain 20% of your money, you would add 20%. So that's kind of the concept we're going to use on this next example here. So here we go. So let's suppose we have a population of organisms. This could be people or bacteria or whatever, and there's 12,000 starting out, or initially there's 12,000 organisms, right? And it's going to be decreasing by 4.5% each year. So we got that decreases 4.5% per year. So anytime you have an increase or a decrease by a percent, that is going to be an exponential function, okay? So it's going to follow this form here, y equals a times b to the x, okay? So remember, a, that's your starting amount. and then the b, that is going to be your growth, or in this case, it's a decay factor because we are decreasing here, okay? So to go ahead and write our function, right, p for population, you can replace the y with a p if you want. For population equals the starting value. That's pretty easy on most of these, right? That's going to be 12,000 that we started with initially. That's our start amount there, 12,000. Now this decay factor is a little bit tricky to figure out with percents, okay? So basically you're going to start with 100% of your money, and for here we're going to be doing this using the decimals, okay? So 100%. So if you multiply by 1, you just get your money back. It doesn't change, right? 1, and then we're going to take off of that 1. We're going to subtract, because it's decreasing, 4.5%. So we're going to take our change our percent to a decimal. So we're going to move the decimal place over 2 spots, right? Move the decimal place over, instead of behind the 4, it's over 2 spots. So our decay factor is going to be 0.995. So the next year there's going to be 0.995 remaining, okay? So that's the concept that we want, is how much is next year. Next year it's going to go down 4.5%, so that means we're going to have 0.995 left, okay? Now, if it's an increase, you would just add that to 1, right? So like an 8% increase would be 1 plus 0.08, so our growth factor would be there because we're adding to the 1, where if it's decay, we're going to subtract our percent off, okay? And then we still have our exponent there, t for time in years. Okay, so here we can say the population is, we're rephrasing the scenario up here, just looking at the equation or the function. The population is started at 12,000, and then each new year there's going to be 0.995 remaining per year. Okay, so that's what's going on with this function here. So just to wrap this up, remember y equals a times b to the x, right? B to the x, the b and the x go together. Can be written this way or it can be written this way. It just depends on whichever one looks better, okay? Right? There's your y-intercept, that's the a, or your starting amount. The growth or decay factor is the b. Now, if we're going to put this onto a graph, we're starting at the a value, that's our y-intercept, and then we're doubling, tripling, or having that value going down, or doubling going up for our graph for the next ones, the next points after the first one. And then that decay factor, if it's a tripling function, pretty simple. But if it's a percent increase, we're going to take our percent, add that to 1 to find our growth factor. Now, if it's a 25% decrease, we're going to subtract that from 1 to find our decay factor. Because like on this one here, a 25% decrease means every year there's only 75% remaining.